Okay. Hi everyone. Today I will talk about, we will look at some reference counting bugs, most of them in the Linux kernel. So we will not look at exploit because it is not part of, it is a topic by itself. Uh, if we want to look at the exploit, we will be looking at the exploit techniques, which will take quite long also. So today we just look at finding out the root cause of the vulnerabilities and also learn about how did they happen. So here in these slides, I put all the links that we will look at. So we'll look at this one first. So this one is a bug from 2017. It is a double free in this DCCP sockets. So before I continue, I hope uh, not sure if everyone that is here came last time or still remember. So I'll give a quick review. So let's look at the demo that we did last time. Okay. So the main idea in reference counting is in programs like C, where you don't have memory management by the runtime, such as in Java or Python, then you have to manage memory yourself. Then one way to do this is to do reference counting, which is in the struct, you have a variable called reference or ref count. And then every time you pass a pointer, every time you pass a pointer to another function or another object, you must increase the reference so that the number so that you know how many references are being held onto this object. Then when you don't want to access this object anymore, so your maybe you change a variable to point to a different address and no longer this one, then you should decrease the counter. Then when the ref count goes to 0, it means that there are no variables holding this pointer anymore. It means that we can free it. Before that, we cannot free because there might be someone still holding this. There might be still one variable holding this pointer, this object. Then if you free, then you might have use after free because there is still an object, a variable that holds this object, holds a reference to this object. On the other hand, if you don't free, then there'll be memory leak, which means that you allocate but you never free, and that means your memory usage will keep going up because you didn't return the memory to the allocator or to the system. So this is the main idea. Then the bug here is, okay, so there are two types of bug, but this concept is the same. So we will just talk about use after free. So use after free bug due to bad reference counting happens when you, what I said just now, uh, a pointer, okay, let's say two pointers, two variables hold a reference to this object, but after removing one reference, we mistakenly free the object. So for example, we have this demo here. Okay, this is not really correct because we didn't really hold any reference. It's just an example of reference counting. So, for example, you see we have this one, enter car. Oh, so at the start, when we create a car, we start with no reference because we say no one is holding it. But actually it is holding up. It's just in this example. But yeah, then we say that when someone enters this car, then we increase the reference. So actually this is not a real life example. We're just doing a demo of reference counting. Then uh oh, this one is a wrong demo. Look at this one. So let's say we have this safe exit where you minus one reference when someone exit the car. But maybe we made a mistake here and we uh accidentally minus twice, for example. Then what will happen is eh, oh sorry. I think it's like this. I also forgot already. Uh okay. So for example here we increase the reference twice. So the reference after these two, the reference become two. Then after we do this wrong decrease, then the ref become zero, and then we free it. But actually, we should just minus one. Then the next time when we access it, it is already freed. Then it will be used after free, and you see the. Okay, sorry, let me enable this. So the when we access it here, you see that the contents here are wrong already because this object has already been freed and this owner field is already contains other metadata due to the fee. Okay, so to summarize, it's very simple. I hope maybe I made it quite complicated, but it's very simple. You just count how many people are holding this reference, and if you count wrong, you will free at the wrong time, and they will be used after free. So okay, I don't waste more time. Let's look at a real example. So in this one, uh, you can look at the bug fix, which is this second link. So let's see what is the fix. So you see the fix is quite simple one. Because what is the bug? The bug is in the current implementation, a packet is forcibly freed if it successfully returned. Blah, blah, blah. Then uh however, if this happens in this situation, the ref count is incremented here and then it still gets freed. So what does that mean? Let's see. So the problem is that it frees too early. But why? So let's look deeper into the surrounding code of this one. So let me try to get the code. Mm, Let's see which line. 606. Yeah. Okay, let's see again what are they saying. So if this is set on a socket, then the address of this is saved to here. Okay, not important, but the ref count and the ref count is incremented. So it is still used. Nevertheless, it gets freed in this process. So quite unclear why they say incremented. Actually, it looks like it's not clear why there's use of a string too early. Okay, never mind. So we go step by step. So let's see first what is consume SKB. So it's not here. So let me try to find the code. See if we can find this source code for this. Mm, okay. So usually this Elixir bootlib is a nice place to find Linux source code, and that you can search, and there are cross-reference also. So this version is what version? Let's see. Uh, huh, I'm also not sure how to check what version. Oh, okay. Okay, maybe as old as 2.6, but shouldn't need to go so far back. So let's try to find out what is the version. Oh, no one talks about the version. Huh. Oh, no, this is wrong. Okay, 4.1, 4.10. So we come here and go to 4.10, maybe just here, and then search. Okay, so it's defined here. Oh, no, it's just declared here. Then check here, define as a function. Okay, so let's see what it does. So consume, which is to free a SK buffer. So what it does is drop a reference to the buffer and free it if the usage count has hit 0. So this is what I showed just now. And then let's see the code. So first is check if it is 0. If it's null, then we just return, because otherwise it will be null pointer dereference. And then next we see atomic read. Atomic read means lagging. Oh, okay, atomic read is means, let's see if we can. Okay, never mind. The atomic read is just read, or if you know about C atomics, then you know. But otherwise, it's just read this as an atomic instruction, using an atomic instruction, and you see, okay, if it's equal to 1, then what do? We do SMP RMB. And then let's see what is this. Oh, okay, never mind. Okay, I think this one is to do a barrier. So barrier is also is for concurrency stuff lah. Atomic and barriers are for concurrency. So I think RMB might mean read modify barrier maybe. Or read memory barrier. Okay, if you are interested, you can go read more about it. But it's to make sure I think it's to make sure that this you put a barrier here so that the instructions cannot get reordered. I think, but never mind. Let's look at the next. This one. So atomic dec and test means decrement and test. So what is the return value of this? Let's see. X86. Okay, never mind. Okay, let's see. So atomically decrement by 1 and return true if the result is 0 or false for other cases. Means that if so first users is the reference counter. You see it checks these users. So when these users minus 1 equals to 0 means that then this will give true. If users is minus 1 equals 0, then it will be true. Then means that if the reference is 1, then okay, let me type out. It's confusing already. So if okay, I copy this here. So here set up a barrier if ref count is 1. Because okay, so the one thing to see is when the reference is 1 means that means we should free. Because after we drop the reference here, and they like to use consume. I forgot what is the opposite of consume, but they usually say consume to drop a reference. I think maybe hold is the other one. I forgot. When reference is 1 means we should free because this is we are the last one that is holding a reference already. So set a barrier. I think is to make sure there are no concurrency bugs. That's the point of barriers. So now let's look at what this means. Atomic dec and test. Let me paste this. We decrease the decrement this by 1 and return true if the result is 0. So if users is 1, then result will be true because decrement by 1, the result will be 0. Then otherwise will be false. So if users is not 1, then we return. Because if user is not 1, then return false, then negate, then return. Then we will, if users is 1, then we don't return. We will call k free. So everything looks correct. Actually, it's correct. It should be correct. But I'm just describing what all this means. So what does this atomic decrement and test mean? It's not very related now, but for reference counting in a concurrent program, it is important to use this because in the Linux kernel, it is a concurrent program. Many threads run at the same time because it's the kernel, it's multi-threaded. So if you imagine we got two threads, thread 1 and thread 2. If you do atomic deck and test, means you atomically decrement and check the result. So all of this happen in one instruction. It's not multiple instruction. It's not for example deck RX then test RX. Uh it's not this. It is instead just one instruction. You can go and check what is the instruction x86 or let's see if there is the instruction here. It's this deck L. So it's just one instruction deck L that does both in one instruction. So it's important because if we don't do this atomically in one instruction, then there might be a race. For example, if T1 is calling consume skb and decrement RX and at this time RX equals 1, then decrement RX means RX equals 0. So you expect test RX to give true that it is 0, but maybe at the same time T2 holds a reference. Okay, let me see what is if you can find the name for opposite of consume. Don't have. Okay. Never mind, then I say hold. Holds a reference. Then maybe it calls REX, increment REX, which is to increment. Actually, it's not even this. It's decrement REX, and then move to some memory REX. So it's many steps. But it cannot be many steps because if at the same time T2 increment REX become 2. Okay, sorry, there's one more. We have to also read. Okay, let me write in pseudocode. It will be load load into REX, then decrement REX, and then store this. Then test to see if this test if REX is 0. So there are 4 instructions actually. Then what if at the same time T2 tries to hold a reference? Then it will also do 4. It will also call 3 instructions. Okay, so now we write side by side. Load. This one is thread 1. I have to do the consume. Then this thread 2 trying to hold. So both will do load. And then this one will do decrement and then store back to here. So this one will try to do the same thing, but increment. Then here got one more. Test if Ix is 0. Okay, then now uh let eh, okay, then now if these two are happening concurrently, then maybe we will see it in a certain order. For example, maybe like this. Okay, so let's see what happens. In this case, we have Ix equals to 1. Let's say we start with this equal 1. So we have load, we have 1. Then here, we load also is 1. Then after we decrement, Ix is 0. Then after we increment, Ix is 2. Then after we save back, Ix, we save, this is 2. But actually, you can see it is wrong already. Because now over here, we store back 0. So it should not be 0 or 2, it should be 1. Because one of them should happen. So atomically means all of these happen at the same time. They should not interleave like this. Then now you test. You test if it is 0. Then yes, so it will free the buff. But this T2 is holding it. So it is wrong already. That's why, okay, so after going through all this, my point is with reference counting in concurrent setting, you must use atomic functions because all this would happen in one instruction and not interleave. Okay, let me come back to this. Okay, so blah blah blah. After if we check that ref count is 1, yeah, to summarize, if we check that ref count is 1, then we free. So we look at the bug, back to this bug. So why is there a mistake? So let's see. Here. Okay. Okay, a lot of things going on. So let's see if we can get any information from the commit. So it says that in this case, receive packet info or here for DCCP packet request, it is free if it is successfully returned, but in this case, yeah, very weird. Why? Okay, let's see what is the size of users. Wow. SK buff. Okay, this one is int. So it's 4 bytes. So it is not overflow. Okay. Okay. Uh, why it's confusing to me because the error, the bug is they free too early. So I thought it means it it decrement too many times, one extra time that it decremented one time more than it should have. But here they fix it by decrementing one more time. So that is a bit weird. Means that they fix by decrementing one more time means okay, I think let's look at what this go to discard does. Okay. So now it's clear. Okay, actually, this is my first time looking at this. That's why I didn't know. But okay, now it's quite clear. So you see what is the code. So this, if you go to discard, then it will just free. So in the original code, okay, let's see here, the original code, they blah blah blah, then go to discard. Go to discard means come here, then just free. Don't care whether there's still any reference to this object. It's just free. But so the fix is instead, oh sorry, it's line 609 is here. It's here, this one. So instead of directly discard, going to discard, here say what they say is it's forcibly free. So you just forcefully free it. Don't care what is how many references are there. So the fix is to don't go to discard, but call consume and let consume decide whether to free or not. And then just return, don't go to discard. Okay, so this is the bug. So turns out the bug is quite simple, but all the reference counting bugs are so simple. But what we can learn from this is uh in code like this that is so complicated, it is very easy to make this kind of mistakes because you see so many if else, then maybe as the developer they also uh, confused already and then forget to use consume instead of directly just freeing. So we see here, turns out there are similar bugs in other places. So let's see this commit. Okay, it's like they say the same thing, unexpectedly free, because SKB is forcibly free. So how they fix? Okay, so this time is different. They call K3 SKB. So let's see what. And here they also say, I suggest to use this instead of this. So okay, later I read this later. But let's see first what is the difference. K3 SKB. So it says, so here it says it's the same as K3 SKB, but some assumption. So let's see. K3 SKB. Here. No. Okay, so just now we see this one, K3 SKB. This one is inside consume. So consume call this one double underscore one. freeze the buffer. So this is something like deallocating. But we look at K3 SKB. Uh, eh, 696. Here. What is the difference? So looks like it's almost the same as consume. Drop a reference to the buffer and free if usage count hits 0. Looks almost the same. I think it only difference is this part, but I think we don't need to care about this. So see, the bug fix is to use this instead of this. But I feel there is another problem, which is they have two functions that does almost the same things, but the name is so different. And one thing about Linux kernel is there are so many contributors. So now you see, it's so easy to make mistakes because of this kind of small confusing details. Then maybe one new developer that come and add new code didn't really know about these things. Then maybe they miss out in the code review. Then they will make a mistake, causing this unexpected tree. You see, so such a simple fix. And let's see what is the problem here, just for interest. So when a socket in this state, blah, 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 if the successfully returns, then SKB will be discarded by K3 SKB. So it's this one, go to discard. Let's look at the code. So here, eh, eh, here. Okay, so before is, okay, look at before. Before it just goes to discard, which is K3 SKB, double underscore, so deallocate. So here we can also see this. Well, sorry, I go through this first. Finish this. So, however, in this case, the ref count will be incremented somewhere. But even if it is still in use, it will be free. And someone still using the free SKB will cause kernel panic. So you see, is even the commit is mostly the same. So it's actually just the same bug. So if you one thing the security researchers would do is variant analysis. So when you find this kind of bug report, maybe you should ask, are there other similar bugs? Then yes, there is one more, which is this, which looks exactly the same. And the fix is also like the mistake is the same, and the fix is also exactly the same. But you see, they are maybe we're not sure if they are reported. Maybe they are fixed by the same person, David Miller, or Masayuki. Okay, different people. Maybe there are different people that fixed. This one is in. Oh, this one was fixed 10 years ago. Means okay, not sure when was this bug introduced, but this bug pattern was already found 10 years ago. Okay, so one more thing I want to show is how code in the Linux kernel looks like. You see, this is the code to handle TCP packets. And if you know, I think since all of us here do security, you should know a bit about TCP packet. which is there are many different fields, and then different field mean different things. So you see most of them just is a lot of if else code, and uh just setting this field to be this field to be this field to be this, or if else. So this is I think we call it state machine, a state machine that has many different states, and then you will just go from one state to the next state, or in this case, actually most of the time you just return or discard. So if one more thing is, if you are doing reverse engineering, and you read state machine code, normally you see the code pattern, it is very uh quite straightforward. So it is a lot of switch case or a lot of if else, and then most of them just assignment, just this equal this equals this. At most, it's just equal arrow or equal left shift n to hs, which is to change do flip the endianness, or call another function, or if else, and equal equal if else. Okay, so what my point here is, a lot of times if you're at least from my experience, if you are reverse engineering a binary, and then when you see a very big function that has a lot of lines, a lot of code, then maybe you will just realize that actually it is just some file passing or passing some data. So like this one, a lot of if else, a lot of equal something minus something, something plus something. The code is very, you realize the code is very straightforward, very simple. It's if else and equals plus minus one. So for this kind, the important step is to find out which if statement you are interested in, and then you just look at what's going on inside. And what is going on inside is also just like this very simple code. This one also very simple because this one is just flipping endianness or free blah blah. But this one is a tip for if you are doing reversing. Okay, last one, then we will call it a day. One more commit. This one is in 2016. TCP SYN packet. Okay, not sure what is this, but I haven't looked at this yet, actually. So here, we now have proper listener. We replace the K3 SKB by consume. You see again? Replace this by this. So you see again, the fix is so simple and the bug is so simple. And actually, for me, I'm not sure why they even have code that calls this. Because actually, there's no logic to call this. You should always call this, because this one is the safe way. Maybe this one is faster because okay, yeah, maybe one way to argue is directly freeing is faster. Wait, but this one is not unsafe also. This K3 it should be you should also check the reference counter. Oh, yeah, this one also checks the reference counter. Okay, this one not very sure. Not very sure why this works but this doesn't work. Why this will have use after free but this doesn't. This is very weird. But I think is what I said just now. Why you got two different functions that do almost the same thing but the name is so different. I think all these confusing details is why there are bugs. Okay, I think it is because if you look at consume, this one it says uh functions identically to K3 SKB, but K3 SKB assume that the frame is being dropped after a failure. So a frame is here, frame is a stack frame, which is when you call a function, then you are in a frame, then you call another function, then you are in a new frame, and so on. So each function call is a frame. For example, it's like a scope. Then here, what perf does is it collects frames. So you see perf record. They are not sure, maybe they don't write it explicitly, but what perf does is it collects frames. Okay, don't have, but what perf does is when you run a program, it will record a lot of all the frames that are in the program. So I think in this payload, it will mess up the frame. Then K3 SKB will mess up. I think not very sure also. Not very sure if this is also, maybe this is just, this is not even a bug. Maybe I'm not sure. Maybe it happens where in certain cases only. For example, when you drop the frame. Okay, yeah, maybe, yeah, I don't know. It's very weird why they have two different functions that do the same thing. Oh, yeah. Okay, so one last comment is one possible reason why people will use mm, K double underscore K3 directly instead of consume. Because actually these atomic instructions are very slow. They are very, very slow. Well, let me show you uh, one moment. So there's this table that's show the cost of each kind of instruction. Then atomics, it takes 15 to 30 cycles. It's quite slow, means that you can do 15 to 30 instructions at the time that during the time it takes to run one atomic instruction. So maybe they call this directly to save 15 to 30 cycles instead of calling this to check. But is it worth saving 15 to 30 cycles for potential bug? Maybe that is something to consider. So I'm not sure if that is why they have go to discard to directly call this and instead of calling consume. Don't know if it's a mistake or it's an optimization. But now you see why C programs are so prone to memory corruption bugs because you got things like this. Maybe trying to do optimization and calling a function that is quite unsafe. Okay. Yeah, that's all for today. I have we have more here to look at, but they are quite complicated. So I think we can look at them next next few sessions. For example, this one is quite long, but it's another similar situation, but more complicated scenario. So I think it's good to look at this next time and a few others also. Okay. Uh, so are there any questions? That's all for today.
Okay, so let's wait for 2 to 3 minutes. See if anyone has any question. Let me stop the recording.
Okay.